Hello physics students, this is Dr. Brenzi here. This is lesson 5.1.5 for AP. And our objective for this lesson is that we're going to explain why engineers build banked curves on racetracks and highways and apply this to solve physics problems. So without a banked curve, let's take a look at what would happen, or the forces acting on a car. So we know that we have gravitational force pointing straight down, Fg, pointing straight down. We have normal force pointing straight up. And the force that is providing the centripetal acceleration is frictional force, which points toward the center of the circle. Now, if this car goes too fast, what's going to happen is that these tires are going to start slipping, and some of you inexperienced drivers may have even come across this on an icy surface. So if we don't have this force of friction, or if this force of friction suddenly reduces because we suddenly hit a patch of black ice, then instead of going along the curve, the circular curve, we're going to end up going in straight motion or nearly straight motion, and we're going to perhaps have a bad day because we've run off the road and perhaps run into something. So is there a way to prevent this, or at least minimize the chance of that happening? Well, what some very clever engineer decided to do one time was to create a banked curve. So this is a curve that is tilted at an angle theta with respect to horizontal. So let's say that this is our angle theta, which means that our normal force, which always has to be perpendicular to our surface, the normal force is now no longer straight up and down, but it has two different components. It has a component pointing straight up, and it has a component pointing in toward the circle. So let's draw the rest of our free body diagram here. We have the force due to gravity pointing straight down. And I'm going to finish this by drawing a dashed line. And if this is an angle theta right here between horizontal and this banked curve, then perpendicular to the banked curve should be also the same angle theta from vertical. So that also is an angle theta. We still have a frictional force, and that frictional force is still actually going to be pointing toward the center of the circle. But now, when we split this into two components, we're also going to have part of this normal force pointing in this direction. So, if I were to split all of these forces into vertical and horizontal components, I have something that looks like this. Well, actually, I'm going to start off with red. So is our gravitational force pointing straight down. That hasn't changed. It's always going to point straight downward in the vertical direction. I still have the force of friction pointing left into the center. But now I have this normal force that I want to break down into components. So let me make that blue. So we have a component going vertically, and that vertical component would be F of n. And watch this, cosine theta. We have the same issue that we had when we were dealing with inclines, in that we are measuring from the vertical axis. So vertical is going to be cosine theta, and horizontal is going to be sine theta. So watch out for that. So there's going to be also a horizontal component pointing in toward the center of the circle, and that is going to be normal force Fn times sine theta. Let me take a quick peek ahead here on my, okay, so I can't do that. Alright, just wanted to see what I could do here on my next slide. So I can split now these these forces and write Newton's second law for each direction. So in the x direction I have F net equals ma. And the net forces that I have in the x direction are negative force due to friction, because it is pointing toward the left, and minus normal force sine theta, and that's going to equal mass times my centripetal acceleration. But my centripetal acceleration is also negative because it's pointing toward the left. That's where the center of the circle is. So I better make sure that that ends up negative. So that's a formula I would end up with. Well, actually I could divide both sides by -1 and end up with force due to friction plus Fn sine theta equals m times centripetal acceleration. Now be careful here, because before you suddenly say, oh well, the normal force is equal to the gravitational force. Be very careful about that, because I'm going to show you that that's actually not correct in this particular case. It's just like an incline. We have to actually look at F net equals ma for the y direction. So let me set that up. Well, what is the net force in the y direction? We have Fn cosine theta equals oops, actually I don't want the equals there first, because I need to subtract Fg. Sorry about that. And that equals mass times acceleration in the y direction, but I don't have any acceleration up or down, so I'm going to set that equal to 0. When I do that, I get Fn equals Fg divided by cosine of theta. So normal force isn't equal to gravitational force, it's equal to gravitational force divided by cosine of this angle theta. And that is what you would want to plug in to substitute for Fn. So if I do that, if I combine those two, I'm going to end up with force due to friction plus normal force times sine over cosine is tangent theta. Actually, that's not normal force. Whoops. Correction. That's gravitational force times sine theta over cosine theta. But you all know what that is. That's tangent theta, right? equals mass times centripetal acceleration, which is m times v squared over r. Okay. So it's not just my force of friction that's equal to mv squared over r, it's force of friction plus the weight of the car times tangent theta. So the larger this bank is, the more that this term contributes to my centripetal force, which means I can go faster for a given amount of friction between the surface of the car and the road. So, a couple of reasons why engineers make a banked curve. First of all, the car's weight is going to provide an additional centripetal force. And this allows cars to go faster without their tires slipping. So you can achieve higher velocities without the tires slipping. Or you can think of it this way. You don't need as much friction force at a given speed, which means it's safer to go around a banked curve on an icy road than it is to try to turn on a flat road. Now, here's an amazing fact. The car can actually turn without the aid of friction. In other words, we could have a completely frictionless surface, and the car can still turn without the aid of friction. So we could actually turn on a frictionless surface. So what might that look like? So if we set up our free body diagram again, force due to gravity, and we don't have any friction force, so I'm not going to point anything in there. So I'm going to assume a frictionless surface, and the only thing that I have here is normal force. This is gravitational force. So in my x direction, I have F net equals ma. And remember, when we split this into its horizontal component, was Fn times cosine. Oh, I'm sorry. That one is equal to sine of theta. Fn sine of theta. And that's equal to mass times the centripetal acceleration. And I better make sure, well, I would have negative signs on both sides if I were keeping track of direction correctly. Sorry about that. Turns out, though, that I can divide both sides by -1, right? And I'd get what I just wrote. Fn sine theta equals m times centripetal acceleration, which is v squared over r. In the y direction, we end up with F sub n. Oops, actually, let me write this out completely. F net cosine theta equals mass times acceleration. The acceleration in the y direction is 0, so F net cosine theta equals 0. Oops, not F net. Jeez, goodness gracious. Whoa. Yikes. Let me back that up. Whoa. It's a little bit too late for me here. Let me try that again. Okay. Normal force times cosine theta minus Fg equals mass times acceleration, but the acceleration in the y direction is 0. So I have normal force equals gravitational force divided by cosine theta, or normal force equals mg divided by cosine theta. Okay. All right, and then we can plug that into here over on the left. So now I have mg times sine theta over cosine theta equals m times v squared over r. And first thing I notice is I have an m term on both sides, so if I were to divide both sides by m, they would divide out. And I have g times tangent theta equals v squared divided by r. So the speed I would have to go at to make this work is given by v squared equals g times r times tangent theta. Or you could say that v equals the square root of g times r times tangent theta. Okay, so what this means is that if you're on a frictionless surface and you have a banked turn, you actually have to go a certain speed, otherwise you will slip out of the circle and crash into heaven knows what. So if you want to make a turn on a banked frictionless surface, you have to go at this particular speed. So if you go a certain speed, though, you can actually make a turn on a frictionless surface. Unlike if the theta was 0, that means we can't, well, our velocity would be 0, right? So, which basically means we could not do any sort of turning on a frictionless surface if we were on a horizontal turn. So, hopefully you learned something about banked curves today. We're going to work with the formulas that we saw in the second slide. We're going to work with those a lot, and I might throw a problem at you where we're trying to make a turn without friction. Anyway, enjoy your evening, and I look forward to seeing you tomorrow. Bye.